map, but then you got to hide that in there, and you got to kind of resolve. It's like a recursive problem at a smaller level type stuff. I have not yet thought of another way to do it that would be better than this. I really don't like this because it really kind of stinks to grab 63 bits from your hidden message to hide it in there. 64 is such a nice even number. But in any case, that was the solution they came up with, and that worked. All right. So any other questions or comments about BPCS? Okay, I think we're doing all right on time this time. Transform domain. In the transform domain, we're going to hide in the significant parts of the data. In the substitution methods, we tried to hide in the noise or hide in places where you couldn't tell. Now in the transform domain, we're actually going to hide in more significant portions. Can be made a little bit more robust than simple substitution methods. Okay. Although the technique that I present here is not robust. If you go in there and mess with the coefficients, as we'll see, then you'll lose the message data. But there are techniques which are very robust. All right. There's a number of transforms that exist. A discrete cosine transform. How many of you have heard of that? Nobody? I mean, I'm sure Dr. Delpa's heard of it, so he's kind of excluded. But okay, all right. What about the discrete Fourier transform? Anybody heard of that? A few people? Okay. Laplace? All right, a couple controls people in here. And the discrete wavelet transform? Anybody heard of that? Just come on, raise your hand high for this. Anybody heard of that? You have, with what? What's it used for? I'm sorry? Image coding. Yeah? Do you know what, well, it's used with JPEG 2000. How many of you even heard of JPEG 2000? Supposedly it's better than the discrete cosine transform, but it hasn't caught on. The programs will probably have an option, like the new graphics programs have an option to save something in JPEG 2000 format, but apparently people are happy with JPEG and they haven't switched over for the slight increase in fidelity or compression ratio. And then a few others, Mellon Fourier, I don't know, some more odd transforms, and I'm sure there's plenty more than that. In any case, for this presentation, you don't need to know about all those, just the discrete cosine transform. And I'll give you a refresher. I'm sure the undergrad students haven't heard about it either. All right, so a little bit about JPEG and how it works. Here we have this 8x8 block again. Okay, so JPEG takes the image and divides it into 8x8 blocks. I'm looking for my mouse cursor here. I don't see it. Oh, there it is. Doesn't seem to want to appear over here. Well, there we go.
It's going very fast.
Okay. All right. There's my 8x8 block. Okay. This is a quantization table, which we'll see again, but it basically converts this colors to 3 different planes. Okay. We get a luminance value, which is kind of a grayscale. So you imagine pulling out the grayscale part of the JPEG, and then a couple of chrominance values. So we end up with 3 color planes. On each color plane, the discrete cosine transform is performed. Okay, and you get a little bit of loss there because, as you know, cosines produce numbers that not repeat, but just continue to have digits and so forth. So you cut it off to get integers. Then you quantize it. That's where you get most of the loss in the JPEG lossy compression algorithm, is with quantization. Then you run length encode it. Anybody know what run length encoding is? Haven't had a data compression class? Okay. Well, we'll talk a little bit about that in a minute. And then you entropy encode it. Okay. And then you end up with the final compressed file. These encoding schemes down here, run length and entropy coding, are all lossless compression techniques. And the DCT and the quantization is where the lossy part happens. So JPEG is actually a hybrid. It actually does some lossy compression, and then it does some lossless compression in the end. And this is basically the words behind what I just said. I guess the last bullet there, a 2-dimensional discrete cosine transform is performed on each color plane. So we'll do that for the luminance values, and it will do that for each of the chrominance color planes. All right, so for more technically minded, DCT is kind of a correlation between the data and various frequencies. And we'll see the formula in a second. So you see, how well does this data correlate with low frequency? How well does the data correlate with high frequency? And that's essentially what a DCT transform is. Really, a Fourier transform is the same thing, except it has the imaginary component, and the DCT only has the cosine component. Also, since the images are 2-dimensional, when you perform this on an image, you use the 2-dimensional version. I guess if you're into advanced graphics and 3D graphics, then you might use a three-dimensional discrete cosine transform. But then the question is, what is frequency when considering an image? I say I'm going to correlate with frequencies. Well, when considering an image, what is frequency?
It's not color.
It's what?
It's not simply the color of the image.
Nope. Not simply the color. Well, I mean, it's related. I know you got colors are certain frequencies on the electromagnetic spectrum, but that's not really. For instance, if I had something image that was a block of red, then there's no frequency there. If I have an image that's a block of blue, there's no frequency there either. Anybody else have an idea of what would frequency mean with respect to an image?
How often a color is repeated in an image?
How often the colors are featured?
How often it will be repeated in an image, that will be its frequency.
Sort of, yeah. I mean, you're kind of on the right track there. Basically, it's how much change is there. Okay, so saying, well, how often does a color feature, then how much change is there? So, for instance, in a grayscale image, you may have some parts of the image that are black. You may have some parts of the image that are white. And so you can imagine if you slowly shaded from black to white across the whole image, that's going to be a low frequency. But if you go directly from black to white, then that's going to be a high frequency because you have a rapid change all the way from white is 255 all the way down to 0, which is black as typical representation. Okay, so high frequency is rapid change. Low frequency is a slow change. A blue sky is going to have a low frequency. A lion in the jungle with, you got the color of the lion, and you got brightness, and you got darkness of the jungle, and transitioning between those two as an example, that's going to be a higher frequency. Okay. The last thing to note, I guess, in the last bullet there is that the DCT spatially correlates the frequencies. That's because typically an image is going to have pixels that, in a given area are going to be similar. Okay, because when you try to compress something, you're looking for pattern. And so if you were just to grab images, pixels from all over the image, the chance of having some kind of pattern is a lot less. And the idea with compression is we want to find pattern and then find ways to encode that pattern so we can encode it in much less space. So that's why you got the fancy spatially correlate stuff. Of course, with video, then you also temporally correlate it. I'll leave that for Star Trek. All right, here's the forward equation for the discrete cosine transform. Need to find my pointer again. I'm moving it slowly. Do you see it anywhere?
Down low, lower right hand.
Oh, there we go. Thank you. All right, it's hard to see because the light is shining in my face. All right, so here's the formula. I know it looks complicated, but it's kind of like calculus. It's easy once you figure it out. All right, a sub xy, that's our point. Okay, that's our pixel image. And for the computer science folks, you may recognize implementing a summation is just nothing but a for loop. So I've got two for loops in here. For y equals 0 to n minus 1, if n's 8, that's 7. And then for x equals 0 to 7. So I've got two for loops. How many times is this going to loop? Quickly. How many times? Louder. Okay, n squared, which is 64, right? 8 times 8 is 64. Okay, so it's going to loop 64 times. And you notice in the cosine there's an x component in there and a y component. So as x and y get bigger, this is going to be a higher frequency correlation. When x and y are 0, cosine goes to 1. And then there's also a u and v component. Okay, u and v is the output matrix. And we're going to get an output matrix of equal size to the input matrix. So u and v are also going from 0 to 7 and 0 to 7. So now, really, for every 8 by 8 block, for the quick-minded, how many loops? We've got 8 squared in here times 8 squared out there. That's 8 to the 4th. So let's see, 8 to the 4th is 2 to the 3rd to the 4th. 3 times 4 is 12. 2 to the 12th. Who knows what that is? 4K? 4096? All right. So for every 8 by 8 block, this is going to actually loop 4096 times. All right. So and then it's multiplied by these scaling factors that follow these rules over here. Okay. So the basic idea is we're going to take in these pixels of an image. We're going to get, let's just say, the luminance plane, and we're going to perform this DCT on it, and we're going to output a matrix. Okay. And the goal is that in the output matrix, a lot of the values go to 0. Okay, so then when a lot of values go to